So first of all, this is a little bit of an experiment. It's the first time actually I'm using my Qualcomm ARM tablet running Windows 10, and attached to it is that Lenaro HDMI dongle. So if anything goes wrong, I'll blame it on the dongle. So with that, I want to talk a little bit about how we run Azure. Azure is the second largest cloud in the world. And as you probably heard, we're doing quite a lot of things with ARM. And so I want to talk a little bit about that as well. I want to talk about how that is relevant to ARM, what we're doing, what kind of things we're building, hardware, platform, software, but also talk a little bit about the challenges. So Azure is a humongous set of servers across the whole world. One of the really differentiating things in Azure is that we go where our customers are. And we do that for a few reasons. We do that obviously for performance reasons, bandwidth reasons, latency reasons, but we're also doing that for regulatory compliance reasons. There are lots of reasons. For example, when you have customer data in Europe, you're not allowed to move that customer data out of Europe. Again, it's a reason for us to have data centers there. We call these combinations of data centers regions. Every region has at least 2 data centers, and we do that for failover, so we can basically lose a data center and still continue operations on the other one. And we currently have regions in every continent of the world except for Antarctica. We're growing like gangbusters. So I think last year we doubled our infrastructure, doubled the number of servers, we doubled our revenue. And to give you an idea of that, I'm going to show you 2 pictures. So here is a bird's eye view of a data center in Virginia. Here you're seeing 2 data centers, various generations. But if you look at those trucks, you get an idea of how big these things are. This happens to be a site where we actually run one of our government data centers. One of the things we do, if you're a large enough customer, we'll actually build a special purpose data center for you. And as you can imagine, it's typically governments that like to do that. We do that in the UK, we do it in Germany. And so obviously we've got some special restrictions around that as well who can get into those data centers. But to give you an idea of how much we've been growing, so that picture that you saw on the previous slide is that blurb that is on the top. Right? Since then, we've built a new data center, and we've clearly broken a lot of ground for the rest of the growth. And that data center that you see there, right at the top, that's actually our standard format that we nowadays use. There are 4 buildings interconnected with an enormous amount of fiber, basically projected for network bandwidth for the next 20 years, because that's typically how long these things last. And we provide, just to give you an idea, 40 gigabytes. At this point, we provide 40 gigabytes between any server to any server in those 4 buildings. Right? So that's sort of the speeds and feeds that we're driving. And clearly, this is growing like gangbusters, and this is one of many data centers that we have around the world. I think at this point, we're probably around well over 150 data centers in the world and growing. So we've been in this data center game for a long time, almost 30 years. And so we started off back in the early 90s with building standard infrastructure. So you put up a 19-inch rack, you build individual servers from vendors, you wire them up to a network. It's basically a hodgepodge of things, right? So they're very labor intensive. They're not particularly efficient. So the metric that you see at the top of this blob, PUE, stands for Power Utilization Efficiency. It's a number that was coined by the Green Grid Computing Organization. And what that is it represents the total power that you spend on a data center divided by the amount of power that you spend on billable hardware or billable components. So this is your computer, this is your networking, that kind of stuff, but it doesn't include things like your air conditioning or other cooling mechanisms that you have, or backup power, those kinds of things. So clearly, a factor of 2 is quite expensive. So one of the things you'll see over the next couple of blobs is that we're actually reducing that to a much, much smaller number. So in 2007, we really started to do this in earnest. And what we started to do really is build custom racks standard servers, but in custom racks, we would all pre-configure them, and we would very much focus on driving the cost down and really getting more density out of it, getting more and more scale. And by the way, one thing I want to point out is that with all of these steps, we grew. And it's kind of interesting that in the data center, someone told me that if you go to medical school, half of the things you learn in school, right, will be proven wrong by the time you're at the end of your career. And pretty much the same is true for building a cloud data center as well. Because you get new insights when you go from 100,000 to 500,000 nodes, when you go from 500,000 to 1 million, and so on, when you go to 2 million and beyond. There are constantly new things that you learn, and we're constantly experimenting things and changing things. So second generation is very much focused on density. How do we pack as much as we can? The third generation is actually where we introduced zones. So we had cold aisles and hot aisles. So you've got cold aisles, that's where the cold air comes in. You would suck it through the machines, through the nodes, and then you would have a hot aisle where you would exhaust it out. And one of the things, for example, that we do is we actually have all the I/O be on the front end of the machine so that the operators actually are in the cold aisle while working on that. Because those hot aisles can get pretty hot indeed. And so you don't really want people to work in that. You'll be sweating like a pig if you're there. That clearly reduced the efficiency a lot. We went actually to 1.2 and 1.5. We then started looking at pods. So one of the challenges that we have is in building data centers is that you build a building, you put it full of machines, but you need to get an occupancy license for it. Even though there are hardly any people in those data centers, you still need to make sure that people can actually get into that building and it's safe for that. And it can quite easily take 6 months or more to get that license. So as we're growing quickly, right, we're building these data centers, we then have to wait 6 months to go and get that occupancy license. So what we started doing instead is building pods or containers. So these are literally, the first one was literally a shipping container, and we put it full with servers, and there were basically 3 inputs: cold water, power, and networking, and that was it. And in Chicago, one of our data centers there, we literally put these things out on a field, wire them up, and we were up and running. The problem, of course, with these kinds of pods is that maintenance isn't that great, or it's difficult. You don't have a lot of space to work in. They tend to be very dense. So with the 6th generation, or the 5th generation, we actually went back into our data centers. But we did focus very much on software defined. So we built smart NICs, pushed a lot of the complexity out into those kind of devices. That, again, drove the PoE higher or lower, so more efficiency. And now we're actually on the 6th generation. And I'll talk a little bit about that in a minute. So but before I continue with that, let me talk a little bit about what our ARM server approach is. So last year, we actually publicly stated that we are evaluating ARM for use in our data center. And we're still evaluating ARM. There's actually a lot of efforts around it. There's a lot of software that need to be ported before you can operationalize that. But the reason we're doing this is somewhat confusing people. I always still get requests or still questions from journalists is like, you're only doing that to drive down the cost, which isn't actually the reason. If it was cost, we would actually just stick with the suppliers that we have. The problem is that we have only one supplier. And so given the rate that we're growing, right, if that supplier ever has a hiccup or anything, or any other kind of challenge, we cannot grow. And that's the situation that we want to get out of. This is not about cost. In fact, if you look at ARM servers, they're probably over time are going to be more expensive than other servers out there because it's just a function of scale. Right? On the ARM side, the scale isn't there, so designing a motherboard, building a motherboard is going to be more expensive than building a motherboard for the commodity part or the high-scale part. So the main reason for us actually is supply chain reasons. We want optionality. We want to be able to continue to grow. We do not want to be blocked growing because we're dependent on a single supplier, and that supplier has an issue. We're also doing it because we want to take advantage of innovation, and we want to actually see more innovation in the server space. And we think that ARM is a much better ecosystem to go and drive that than anywhere else. And obviously, it also helps that we do have things like client builds, Windows client, which is still what a lot of other applications depend on. So it's a much easier porting effort for us than anything else. So we're also interested in creating a healthy ecosystem. We're not interested in one ARM server player. We're interested in multiple ARM server players. So we're working currently with 3. 2 of them have been public, Qualcomm and Cavium. And we actually, there's a 3rd one who wants to remain anonymous at this point, although probably most people in this room know who they are. And then there is actually other ones that we have enabled too. I mean, ARM, for example, on the things they're doing are running Windows Server. Ampere actually just showed this week at OCP Summit back in Santa Clara that they're running Windows Server. So we are interested in Windows Server, but we've only been doing that for internal use. And that is another thing that I've gotten a lot of questions over. The reason for that is where we see the opportunity. Right? Taking on and building an operating system and providing a 10-year life guarantee for that is quite a commitment. Now, if we look at this market, right, we see a growth on cloud, tremendous growth on cloud. The CAGR is around 40%. If we look at enterprise, standard enterprise, there is basically no growth. It's a stabilized market. So from our point of view, the opportunity isn't in enterprise, right? Moving a stabilized market to a different architecture is extremely difficult and expensive. And we just, for now, we don't see the opportunity. Now, obviously, if that market were ever to materialize, we have the capabilities. But for this point, at this point, we're not doing a retail version of Windows Server. We're only focused on our internal applications. The key focus is on internal cloud applications. And with that, I mean applications like search. You can think of it as SQL services, all those kinds of things that where we actually control the stack and it doesn't expose the x86-ness, right, that you see in VMs. So the traditional VM hosting business is not something that we're seeing going to ARM anytime soon, unless there is an ecosystem around that that builds up. But without that ecosystem, we're just focused on the internal applications. We're also developing hardware. One of the things we do is we actually build our own servers. We do that for cost reasons. We do that for quality reasons. And so we're doing the same thing in the ARM space. And I'll show you some pictures of it later on. So where do we see the opportunities? Well, I already mentioned search and indexing. We got a lot of servers devoted to that. High-performance storage is an obvious candidate because, again, the stack is what we control. There are no user applications running. There are no user VMs running. It's all our own code. Machine and big learning, obviously, is taking up a larger and larger percentage of our data center capacity, and so on. Platform as a service, again, anywhere where the ISA doesn't shine through, right, is actually a good candidate for ARM servers. And when I talk about ARM servers, the ones I'm working with are building high-end, high-performance servers, because that's what I'm interested in. I'm not interested in putting a bunch of A53, Cortex A53 together, because that's not sufficient for my workloads. Most of my workloads still benefit from single-threaded performance improvements. Now, if you add all these properties up, it turns out that's well over 50% of my data center capacity. So there is actually a very good opportunity for ARM servers. Now, obviously, there needs to be a value proposition, right? So that, I think, is the one that we are still having challenges with. So here's an example of what we have done, and I'm sort of focusing on Windows Server that we're running. The pictures that you actually see here on the side are Task Manager running on a Cavium box, a Cavium 2P box. And the only reason I'm showing that is because it's sort of cool to show up 256 hardware threads executing. But obviously, we have similar kind of things on other hardware platforms running. We do have Windows Server builds, again, for internal use. Both core and full is what we're building. We actually have the full compiler support. That's actually part of Visual Studio 17 that you can actually download, and you can use it on those client systems as well. We're integrating Hyper-V. We actually have over 500 ARM servers in Microsoft for our internal developers. So that's what we're using to develop, performance testing, all sorts of kind of things that we're doing with that. In fact, we've got so many ARM servers that we're even surplusing some of the ARM servers right now because they're too old and too not very powerful. And we have got, of that list that I just showed, a number of those properties are actually evaluating ARM server. So what's still missing? A lot of performance optimizations. Right? The benefit of the x86 ecosystem is that you've got about 30, 40 years of performance optimizations, both in the compiler and libraries and other parts of the system. We're missing that on the ARM side, and we're definitely seeing that. The other thing where ARM is actually running ahead of some of the x86 architectures is the high core count and the interesting NUMA properties that come with that. Once you start running 256 threads on a single box, hardware threads, there are very interesting things that happen in the OS. Windows definitely has its share of issues in the scheduler and stuff like that. My understanding is that Linux has a lot of the same kind of issues. So it's kind of interesting that we're, with ARM platforms, running into that first. OK, Project Olympus. So Project Olympus is a hardware project, and think of it as a modular approach of how we build hardware. So we build our own hardware in Microsoft for cost reasons, for reliability reasons, for support reasons. We really like as much uniformity as possible. And so we built standard chassis. In that goes a pretty standard motherboard. Yeah, we put some other things on it, but overall, it's a standard size motherboard. And where we really differentiate a lot is actually in the power supply. So when you're in every continent of the world, one of the biggest challenges is actually get power in all those servers and do it in such a way that you can build one SKU of servers and deploy them everywhere. And so the way we've done that is we've actually built a special power supply. It gets 3 phases of input. And really, the only thing we change, these racks go everywhere around the world. The only thing that we change are the power connectors that you see on the upper right side there. The nice thing about this modular architecture is that for ARM, I only have to focus on building motherboards. Right? I do not have to build an entire server. It's one thing to figure out how do I get ARM into Azure. It's another thing if I had to build standard servers with that I would wire up to everything. It has all our secret sauce in it and that kind of stuff. I don't have to deal with that. Right? I built a motherboard. And those motherboards we've been building 3. We've had one with Foxconn and Cavium. We built an earlier one with Inventec. And we've also been working closely with Qualcomm, as you saw with all the announcements in early 17. And again, the nice thing about these motherboards is they just slot into our standard machine, so it just fits in our standard deployment model. They're the same size, the same configuration roughly. So our operational people know how to deal with this. So let me talk about some of the challenges in the ARM ecosystem. I know you guys, as an organization, have worked on this a lot, but standards are an absolute requirement for ARM64 adoption at scale. And it's also an ongoing dialogue. It's not something that you've done once and you sort of stuck, because there are new things that we learn. And there are, like, for example, recently ACPI introduced something called the PPTT table. It's a new way to describe NUMA nodes and how caches relate to everything. This is how operating systems optimize things. This was actually driven by the ARM folks, and we actually are using this, or planning to use this, on the x86 side too, because we see a lot of the same challenges that the ARM systems are sort of running ahead with on the x86 side as well. But that standardization is absolutely critical. Hyperscale is about increasing scale and reducing complexity. Right? When you've got very complex solutions, time scale, that doesn't work at all. So we simplify things a lot. Again, that's why we build our own systems. And that's both from a technology point of view as well as a supply chain. So you see me speaking out very publicly around things like OpenBMC, things as UE80K2. because when I deal with my partners, if I have to add a third one to it or a fourth one to it, like an IBV, right, it increases the complexity for me to manage all of this. Sticking to the standards that we already know and love, well, love perhaps not for everybody, but definitely know and support, that reduces the friction. It reduces the barrier to entry. And one thing that has been quite complicated for the ARM ecosystem is that, frankly, hardware bugs and non-standard design are not my problem, right? That's why I'm developing multiple. And if you've got a hardware bug, you fix your design. I'm not going to change my operating system because I can't deal with having multiple hardware fixes or hardware workarounds in my operating system. And that has literally happened. I have forced partners of mine to do an entirely new spin-out, a tape-out of their part, and put some new major functionality in it quite late in the game because they were non-standard. Still, there are a lot of business challenges. So we're sort of at this interesting spot where we're finally seeing capable ARM servers, definitely sort of at the Broadwell level, and hopefully next year we're going to see some better ones that are even getting higher than where the other competition is. But unfortunately, there's also a lot of server fatigue in the industry. Right? When I go and talk to, I spend a lot of time talking to my fellow cloud vendors or my fellow cloud partners. Because, yeah, we're competitors, but you know what? There are also areas where we're also looking for collaboration. Because in the end, we're interested in commoditizing things like, for example, hardware, right? We all benefit from scale. And some of these companies have been experimenting with ARM for over 10 years. And they started out with 32-bit processors, and it didn't cut it for their workloads. And so their senior management remembers that. Right? And so you have to overcome a hurdle with them, which is quite challenging. I still get a lot of complaints that there are no ecosystem that provides turnkey solutions. Again, I talked to a second-tier cloud provider here in China in last November, and they said, yeah, workload-wise, the performance is there. It's sufficient for our needs, but we pull down apps and we try to compile them. It doesn't compile, right? Or we need this particular component, and there is no ARM version for that. So I think that's sort of our next challenge, to get that level of support in there. Now, from my perspective, I go after applications that I control, right? And even that is a challenge because Microsoft has a lot of code, right? And so things like, where on the x86 side, we have optimized encryption algorithms, optimized CRC checksums. None of that stuff exists on ARM. So that's where a lot of our effort is going. The other challenge is still there. There's a lot of consolidation happening in the semiconductor space. And that actually is making the ARM server future pretty uncertain at this point. OK, so let me summarize. So I think that as an ecosystem, we've made good progress, both on the hardware and the software front. As I said, we've been driving hardware vendors to make changes to it. There's been an enormous amount of enablement on the Linux side, largely through this organization, to go and standardize that. And those standards are paying off. Just to give you an example, all the ARM partners I've worked with so far, we always required some fairly deep debugging, both in the Windows to go and figure out firmware bugs, or in some cases do some Windows workarounds, although I earlier said we don't really do them. Obviously, it's not entirely a black and white story. But all of them, we had to do something special with them and work with them and get things to fix. Last year, Ampere came to me. At that point, they were still APM, and they said, we want to run Windows. And I said, look, I'm not unable to support you, right? I've got already my hands full with my team. I can't take you on. I'm happy to give you access to the binaries, but you're on your own. And so they went away. They came back 6 months later, and they said, we think there is a bug in Windows because we can't boot from SATA or the direct attached SATA, which is the SATA attached to the AXI interface. And I said, nope, it works on other systems. Literally, that was the only thing I said. It works on other systems just fine. And they went away, came back the next day and said, yep, we found the problem. It was in the firmware. We fixed it. And they brought it up. They were the first ARM server partner that brought up Windows without any of our help, which is a big deal. Because unlike Linux, where you can look into the source code, or you can modify the source code to make it work, because I've seen it a lot too, with Windows, you just get the binaries, and you don't get to change anything, and you don't get to look into the source code. So I think that's a testament for the standardization efforts that you guys have been driving, and they're actually paying off. So from a Microsoft Azure perspective, we're maturing. We're focused, obviously, on targeted applications, OS, tooling, workloads, that kind of stuff, as well as the hardware designs. There is sort of an interesting stage at this point, since Microsoft has been the first one, and so far the only one to go public on ARM servers. All of Wall Street is looking at me to make this thing a reality. So really my focus is on deployment inside of Azure, and I'm not going to make any statements about that here, by the way. But as I said, those business challenges still remain. So I don't know whether we've got time for questions.
Yeah, I think we can take a couple of questions. Really fascinating stuff. Do you have a hand mic that we could use, maybe? Great. Anyone? Really? OK, why don't we start right over here?
So when you see the, there is a reason of supply chain, so how do you see the AMD servers?
Oh, AMD is very much part of our strategy as well, right? But what we're after is optionality, right? The challenge a little bit on betting on an ecosystem with a duopoly with only 2 players, where one can outspend the other significantly, right, creates lots of business risk as well. Now, on the other hand, AMD is much easier for us to adopt because there is no software hurdle, right? So, but they're definitely part of our strategy as well. So we have a multi-pronged strategy that includes both. And don't forget, Intel is our biggest partner, right? We work very, very closely with Intel, and they've been a very good partner to us, and we'll continue to work a lot with them. So it's not like we're actively trying to get rid of Intel. It's just that from a business perspective, right, for us to grow, we need optionality. So.
Others? Really? OK, right down this end.
If there are no more questions, I just want to have a little bit of a shameless plug. At 2 o'clock today, there is a panel where Linder is going to be part of with some other folks from the industry that are well known in this crowd. Come on down, ask these questions, think of questions, and we'll be happy to host you there.
Go ahead.
Do you think Microsoft would participate in the consolidation within the industry?
So I'm sorry, I think you had a lot to drink last night, so I'm not quite sure.
Not enough. Yeah, do you think Microsoft would participate in the industry consolidation as a way of potentially protecting itself and its investments?
Well, that depends on how it plays out, right? I'm not really going to comment on that here. But we definitely have the ability to do that. The real question is, does it make sense for us to do that? Right? I think on ARM, what we want to see is an ecosystem with multiple players. That's why we're enabling more than one. We are expecting to see some consolidation. I think what we're seeing today is a little bit more than we had anticipated. So I'd like to leave it at that. So.
I think we have time for one more. Anybody? OK.
Okay.
Linder, thank you so much for joining us. That was really interesting and insightful. OK. Please join me in welcoming Tomas Evensen, who is the CTO for Embedded at Xilinx, and he's going to share all sorts of interesting insight with us about FPGAs. Welcome, Tomas.
Good morning, everyone. So I'm going to talk about FPGAs. Just show of hands here. Who knows what the heck an FPGA is? That's quite a few people. Who knows how to use it from a software point of view? Not as many people, yeah. So being a software guy at Xilinx is obviously interesting. And what I knew about FPGAs before joining, really, the FPGA part Oh, that was for the hardware guys, right? I was more interested in the embedded processors. And we'll talk a little bit about that, but mostly I will talk about the FPGA part and how you can use both together. And the really fascinating and interesting thing that's happening right now is software guys are actually programming the FPGA for accelerators and so on. So I'll get into that a little bit here. So the reason why people are looking at FPGAs, of course, is we've all seen this before, right? Moore's law doesn't really apply that much anymore. It's harder and harder just to add CPUs. Even if you add many of them, you get power issues and so on and so forth. And the workloads, of course, at the same time are really exploding. So I think a lot of people have realized that you need specialized execution engines to be able to handle all these different loads. The problem, of course, then is, well, if you have one really specific execution engine for one task, another one for another task, well, how do you do that? Because very often you want to have mixed loads, like in a data center, for example. You can't have one specific accelerator for each task because there's so many of them. So then FPGAs as programmable hardware, is what it really is, comes in, because you can use the same board for a lot of different things. So you can even time slice it. So you use it for some acceleration first, and then you use it for other types of acceleration later on. And this applies both in the cloud. So Amazon and other people, they have FPGA servers, basically, or the cards by the servers. There's the F1 from Amazon, for example. But then also in the edge, things like driver assist, ADAS, autonomous driving, embedded vision, and so on. Lots and lots of people are using FPGAs for that. So today I'm talking about what we call Zyng UltraScale plus MPSOC, and that's a mouthful. I did not come up with the name. This is a really interesting chip from a software point of view because there are lots of moving parts, lots of stuff where you can put your code, if you will. So for example, you have some A53s. So this is really more for the embedded space. And A53s are more than well enough equipped to handle those tasks. When you want to have a little bit more oomph and for compute and so on, we put that into the FPGA part of it, right? So you have 4 of them, typically running Linux. Sometimes people put a hypervisor there and have multiple operating systems and so on. We also have some real-time cores, so Cortex R5, 2 of those. In a lot of these systems, safety and security and those things are really important. So these guys you can run in lockstep, for example, which is really important for safety. Also for real time, if you really want that low latency between the FPGA and the core and not have things like caches and so on get too much into the way, then the R5s are really good for that. You have memory, of course, GPU, peripherals. A lot of what FPGAs are really good at is really high input-output. Very often what people do, they have something coming in, maybe from an antenna or something like that, or a video stream, and then you go broad in the FPGA. You can go really broad and have really wide buses since you really design your own buses in the hardware. Right? So you can have packets coming in, for example, and then you go 256 bits wide and go through the fabric while you do your recognition or classification and so on. On some of our chips, we have a video codec. We have a couple of interesting other processor units for security and platform management. So these are triple redundant processors, are supposed to be up and running all the time, of course, right? So you put your boot code, secure code, and so on. You can put them there if you want to. But then we have the fabric. So for some reason, we can't even ourselves come up with one good name. So FPGA, programmable logic, fabric, it's all the same. It's the stuff that the hardware you can program, basically, right? FPGA is a pretty old term field, programmable gate arrays. So I don't know how applicable that is. So very often you hear these terms, programmable logic, fabric, just interchange one with another. So the question is then, all right, this fabric, how do you program that? And what is it really, first of all? So that's the interesting thing. When you ask people, what is an FPGA, you very often get really different answers depending where they come from, what kind of background. So it started with FPGAs really being, what we call the LUTs, the lookup tables, so programmable logic, your NOR and NAND gates and so on, you can program them yourselves, and then you can change that. So it's really hardware that's programmable. And then people came up with, well, we're using a lot of these guys just for memory. Let's put in some hardened memory. We actually have multiple types of memory with multi-port accents and things like that. Next thing, people started to use these for things like multiply and accumulate and so on. Well, why don't we harden that and put a lot of DSP blocks? So in some of these, you have thousands and thousands of these DSP blocks into the fabric in various places, right? So that's been the trend, that you harden more and more things, which means that you can use this for the glow logic. That's sort of what it started out. So if you have your own type of bus, or very often in industrial applications, you have different types of buses, field buses, and industrial Ethernet, and so on. So you can, with the same chip, you just reprogram how you interface with those buses, right? So that's one way of doing it. Not too interesting for a software guy like myself. But those DSPs in there, if you can really parallelize your matrix multiply or your, what we'll get into a little bit later, neural networks and so on, that gets really, really interesting, right? Other people, they knew FPGAs from simulation or emulation. So we have these really big FPGAs, and then you put like 8 of them on one board, and then you can simulate new ASIC designs. So some people, that's what they do and what they use the FPGAs for, right? So that's the interesting thing. You can use it for a lot of different things. But since it's so programmable, you can have your own buses, as I mentioned, your own data flow. It's really good for things like machine learning, where there are lots of experimentation right now, lots of new ways of doing stuff. You can sort of have intelligent memory that's serving up all your weights in a really nice way, so you don't have to go out to memory all the time. So lots of innovation happening right now around how to use FPGAs for machine learning and a lot of other things. So how do you program this stuff? Right, so it used to be that really was something for the hardware guys, and they had their funky languages like Verilog, VHDL, those kind of things, right? Interesting languages, but a little bit harder for a software guy. We tend to think a little bit more in the serial fashion. There, everything's happening at the same time, right? So you really have to think in a different way. So, but if you want to program them with that, that's great. And for some tasks, that's absolutely the way to do. What we've done over the years is adding other tools on top of it. So we added the C compiler. In the beginning, it was mostly for the hardware guys, but they wanted to write it in C, but still they had to connect it with other things and so on, and do all the glue and all that stuff themselves. So you really had to be a hardware designer to use it. But you could take your C code, it will unroll your loops and so on, and if you did things like matrix operations and so on, you can really go wide and go 100 multiply accumulates per cycle and things like that, right? What we've done later, the last few years, is then add another layer on top of it for software guys like myself. So now you can write your C code, and then you can just point to a function and say, hey, I want this one to run in hardware. If you just do that and nothing else, it will probably run. It will probably not run that great if you haven't thought about things. I mean, you would never do something like parsing a linked list in an FPGA. It just doesn't make sense. You want to have the data concise and close to each other and things like that, right? But if you know what you're doing, it's a little bit like programming DSPs. You have to understand a little bit of the hardware underneath. But once you know that, then you can apply some pragmas and things like that. You can yourself specify, how do I want the data movements to happen? Should I use a DMA? Should I plug in a new DMA myself? And so on and so forth, right? So an example of that, so the tool that's doing that in the embedded space is called SDSOC. And we have a similar tool for the data centers called SDXL. Kind of the same infrastructure underneath, but different use cases. Because here, we're running part of the application on the embedded ARM cores and part of it in the fabric. So if you imagine a really stupid program here that's not really that great because someone forgot to initialize the matrices here. So they're doing multiply and add on something that's unknown, but hey, it had to fit on the slide, I guess. So what we're doing here is really, so this is more pseudocode, of course. So you're doing a multiply B times D to A. And these can be really big matrices, of course, right? So, and then you take It's actually A times B to D, and then you take D plus C. So it's just a regular multiply and add, a MAC operation, into E. And then on the command line, or you can do it from the IDE, you just point to these two functions here and say that, no, I want these two guys to run in the fabric instead. What the compiler does, and it looks like a regular compiler, you have the same options and things like that, right? What it does then is under the hood, it compiles the rest of the code with regular GCC or what compiler you're using, put that on the ARM, you get an L file out of that. The other stuff, under the hood, it pushes that stuff through our HLS compiler, which is a high-level synthesis. It takes the C into RTL, which is the sort of the language of the FPGA. And then it builds all the different stuff, all the glue in between as well. So in this particular case, it's kind of interesting here, that you have to get, obviously, the first two matrices into the multiplier. There you can specify yourself if you want to use one DMA for those two, or separate DMAs, or if you just want to copy it to main memory, lots of different ways. So we have really made the data movements a first-class citizen. You can really specify outside of the code itself how you want to move the data back and forth. The compiler is smart enough to see that, hey, D is the output of one of these blocks here. I really don't have to go back to memory. I can just stream that into the adder there. By doing this, you can imagine if you have a video pipeline and you have like a Sobel filter and a corner detection and something after another, you can actually write that all in C, but all the data movement, everything real is actually happening in FPGA, just shuffling the data from one block to the next block. So it's a really interesting way of doing it from a software point of view, but let the hardware do all the hard work here. Another really interesting thing with this is, it's a little bit, when I started programming, which was back in the 70s, the compilers were not that great. So very often, even if you used like C, for example, very often, if you were a nerd at least, you looked at the assembly code and you said, hey, I can do better than that, right? You didn't do that for everything, but if it was something that you really wanted to run fast, you wrote your own assembly code, if it was a 68,000 or something like that, right? But you didn't write everything, and you still had a linker that linked everything together. So you can do the same thing here. You can start putting a lot of stuff in C, put it over there. If you're not happy with the code, you can then have someone, or yourself, if you know Verilog or VHDL, replace that part as long as you connect to the XC interfaces the right way and make that sort of a library that someone else can use. So that way you can work together with your hardware guys that knows those kind of languages and use this tool more as a way to glue things together. So then on top of that, we have added other things. So like for machine learning, for example, people are not really writing all the matrix multiplying so on themselves. They're using Caffe or TensorFlow and so on. So we have interfaces from that then generates either for our data center use case or our embedded use case. And that way, it's really a nice way because then we and our partners can work on optimize the neural networks that gets output from Caffe, for example, right? So as a programmer, you really don't have to know anything about FPGAs at all. We also have a bunch of other libraries like OpenCV, FFmpeg, and things like that with accelerators in the FPGA. So from a software point of view, it looks like just another accelerator, just a library you call, basically. And that's really where we want to get to, is that for most software people, they just call a library and things will run fast. And then you have some other people that are really good at writing those accelerators into the FPGA. And that's what the tools allows you to have that separation between those things. So here's another machine learning example from one of our partners, DeFi. So this is the interesting thing, of course, as you guys know about machine learning, is that you have all these different kinds of neural networks, and there's a lot of new innovation coming, and FPGAs work really well with that because you can really design your own hardware so that it really fits to it. In this case, they have an SSD network, so that's the single-shot multi-box network. And so they're comparing that with the NVIDIA GPU, and we get 5 times the performance per watt performance. And very often, raw performance is really important, and you can get that, and you can use really big FPGAs for that. But very often, it's performance per watt, right? For example, if you have a camera in a car, you can only use like 5 watt or something like that for the camera that's front-facing. So it's really the compute you get per watt that's really, really important in many cases, right? So as we heard 2 days ago, what we're doing now is that we're launching a board called Ultra 96 that will sell for $249. And this is really the first time. Before, our boards that we've been providing ourselves have been bigger, really showcasing the FPGAs with all the I/O and so on. This is really meant for software guys to experiment and work on. And it's really cool. I really love this board. I've been using it quite a bit myself. And you can use it in many different ways. You can use it like a Raspberry Pi kind of like thing. You just connect to it either over wireless, or you can attach a monitor and a keyboard, and then you just do GCC and you do your make and everything on the board itself. Really easy to get going, and lots of examples and so on. Or you can download our cross-compilation tools, our cross-environment, and then you get the full Eclipse IDE where you can do debugging over JTAG and things like that, and all those tools are available for free there. What we also have is the SDSOC tool. So that will come in a couple of months for this particular board. It's not ported to this board as of yet. But then when you get this board, you will get a 1-year free license for that SDSOC tool as well. So this is really fun to play around with yourself, because you can, as a C programmer, C++, or OpenCL, you can write your own code and see what heck happens, and really fun to play around with. And since it's so fun to play around with, we're actually going to give away 30 of these on Friday. So we're having this contest coming up, so I really encourage you guys to look into this. So what we're going to do, you can come to our table on Friday, come up with a proposal on, hey, this is what I would use the board for. And then we'll pick the coolest ideas there, 30 of them. And then you have some time to work on it, right? And then you can submit something later on, and there will be prizes and so on for that. So kind of a fun thing as well, but we really want to get this board out for people to really experience the FPGAs, because it is a little bit of a new way of thinking, of course. So I'm going to end with a little demo, so if you guys can get that up, and it's still running. You never know when you're up here. So what are we doing here? So this is yet another type of network. This time it's a binary network. Binary means that all the weights and the activation function are just a 1 or -1, basically. So only have the 2 values. And as you can imagine, one of the advantages with an FPGA is that you can have this mixed precision. Obviously, you can do 32-bit stuff. You can do much bigger. You can do 8-bit. You can do 1-bit. It just means that it uses a lot less of these LUTs and the DSPs that's in there, and that the power consumption goes near dramatically, of course. The nice thing with binary network is that you can use bit operations instead of multiply, right? You do the XORs and stuff like that. So it's kind of interesting. And that way you can have deeper and bigger networks and get similar precision as opposed to a regular network. What we're doing here, we programmed this with road signs. For some reason, German road signs, because there was a database of that. So we put that through training in Amazon. So people always ask. So it cost $7.78, I guess, to do the training for this thing. And then we take the output of that, convert it into a binary, the weights and so on into binary, and then we run it on this little board. So this is the board that we are, Ultra 96. It's one of these small ones that has the same, it's the same form factor as the 96 boards, of course. And the performance is pretty amazing. We are actually running in parallel on the CPUs. And again, binary networks are not that great for CPUs, right? So it's a little bit of an interesting comparison here. But what we actually get is like 19 or 19,000 frames per second. Actually, right now here, I see we get like 14,000. So I don't know if the electricity is a little bit weaker here in China or something going on. But say 15,000 here, while we get 94 frames per second on the, or tiles per second, 2.2 tiles per second, I mean, which means that it takes 92 seconds per frame to run it on the CPU, and you can do 94 frames per second on the FPGA. So then you do the calculation. So when we ran at that time, it was 8,600 times faster, which is a big deal, right? It's a pretty big deal. And so what it's doing is and then we went out and took a bunch of photos, and we're running through that. And I'm told that it actually has a couple of errors in here. I haven't really been able to detect them, but some of our guys say that there are a couple, you know, how it works with neural networks, you don't always get it right. If you want to know more about the stuff I've been talking about and are interested to go a little bit deeper, then Glenn is going to make a couple of presentations here. So one is today at 4 o'clock, talking more generally about accelerating things on an FPGA, and then more talking about the neural networks tomorrow at 11, right? So I don't know, do we have time for maybe a couple of questions?
Yes, I think that we do. Does anybody, any questions for Tomas? Mad Dog?
Not so much a question, but one thing you didn't really point out is that the FPGA not only speeds up the calculations, but offloads the main processor from having to do it. So your main processor can be concentrating more on other things.
Exactly. So one of the whole ideas, and that's something you can do with these tools as well, is to really make sure, part of it to get the speed up is to get the pipelining going so that you feel the FPGA with doing stuff all the time. But then, of course, you have then the processor free doing other stuff. And Glenn will talk more about that in his sessions as well. Good comment.
Anyone else? Oh.
Anyone here?
How much time have you spent on streamlining the feature detection process whilst creating a model, the machine learning model?
So how much time do you spend to
Have you managed to streamline the process of feature detection when creating your machine learning model, say, for image classification?
Not sure how much time we spent or how much...
Have you been able to, because a lot of time, in part of the machine learning models, a lot of effort is spent into feature detection, actually defining what features you're looking for.
Yes.
So I was wondering if you have managed to streamline that process, or that's
all right,
still...
now we get, sorry, it took a while to, yeah. I mean, the interesting thing here is that the training, really, you do that the same as with any other, right? You use the cafe and so on, you run it on Amazon or other servers to do that. So that part we haven't really changed at all. It's really the inference, the actual execution of it that we are accelerating more at the edge in this case, or in the cloud as well. So, but the training part, we're not touching that really.
I see,
yeah.
okay.
Yeah, good question.
Anyone else? Yeah.
When you provide all the standard acceleration libraries like the FFmpeg or other blocks, do your customers have to write custom drivers for every application, or is there a bunch of drivers that you provide and that you have upstreamed?
Yeah, no, so what we're doing is if you're using like our OpenCV libraries or something like that, right? So that comes, so from your point of view, so those are in open source, so you can go and see, and they're written. So for example, the neural network, binary network for this is written in C actually, so you can look at the code and see how that looks like. And then for interfaces and so on, the tool will take care of the interfaces. So what you basically do is saying that I want to have this library and this library, basically calling those libraries. And then it will create the bit stream, which is the FPGA, and the interfaces will automatically be created. If you want to, you can then go in and change the default to something different if you want to have you know, a different DMA or have multiple DMAs so that you can stream a little bit better. But so typically the flow is that you get it going first, so you just compile and get it going. Then we have tools, and we'll talk about that a little bit later in the other sessions, where you can see exactly where you spend your time on the buses and so on, so that you can go back into your code and change a little bit so you can really streamline, so you overlap the transfer of data with the compute of data and things like that. So that's really what you spend your time on when you use these kind of tools to get it faster.
Sorry, so since your application scenario, you mentioned a lot about neural network inference scenario. And in today's a lot of inference engine, they use the standard libraries like gymloP. So the one thing I didn't quite get is, do you expect us just compile that gymloP and then your cross-compiler do that, or you have prepackaged some of those somehow we just link?
Yes, so we have, so for example, for Café, and we're coming up with TensorFlow and so on. If you're using those, we are doing all the, everything underneath. So we're taking the output of that and then doing all the work to get it into an efficient bit stream. And then we have roadmap of other libraries and frameworks that we're going to support going forward. So the intent is not that everyone should implement that by themselves. But still, it's fairly early on, so it's just the most popular ones that we've done. And then we have partners that's doing a bunch of the other ones as well. So there are quite a few out there already, some that we are doing, but then we have some partners doing it as well. Or you can also, of course, feel free yourself to do the lower level and experiment with that as well, because there are different ways of how you want to get the data through the FPGA and so on.
Yeah, let me just probe a little bit on that same line. When I accelerate the inference, I could just accelerate one particular operator in the network, for example, COM2D or accumulate add, or I could really extend and make it powerful to take, for example, doing inference on the whole graph. Do you have any, which approach you're thinking? Which is the best way of using your engine for that? Yeah,
so currently what we're doing is actually you sort of design your own network, and you use one of these frameworks, and then we take care of that. We are not really at this point helping you decide if it's better with a binary network or with a different kind of network. That's sort of up to you at this point.
Okay, thank you.
Okay, so I have one final question I'm curious about, and I think it's an easy one. So I'm just curious, are Spectre and Meltdown a risk factor in the world of FPGAs, or are they really not a consideration?
No, that's the nice thing with FPGAs. So they are really nothing like that in there. If you vulnerabilities like that, really it's more an issue when people know when using the same thing. So we have ARM cores in there. On this one, we have the A53, where Spectre is not an issue. FPGA fabric itself, you can put processors there, and we have our soft cores. They don't have those kind of issues. But the rest of the code is really your own code. So if you have vulnerabilities, well, first of all, the person trying to attack it has to know what the heck you were doing in FPGA. So that's a big, because they can't easily get to the bit stream, right?
Right, thank you. All right, Tomas, thank you so much. That was really interesting. Okay, so we're going to take a little break. We'll start again at 10:30 in here for enterprise, HPC, and AI machine learning, and ecosystem day, and next door for automotive, mobile, and embedded. So have a great day, and we'll